Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. I hope that everyone had a great International Women's Day and enjoyed part one of the Women in Engineering segment on this podcast. Last week, I talked about the statistics of women in engineering, and if you remember, there were far fewer women in engineering than men, specifically less women in management and leadership roles. Now, I do want to mention that the purpose of these segments is not to say that men are bad. I don't think that at all. You can elevate women without putting down men. I just think that different people from different backgrounds each bring something unique to the table, and the more diversity we have at the table, the better our collective ideas will be. Last week, I touched on the limiting factors that can contribute to why there are less women in engineering. I'm going to recap those first, and then I'm going to talk about some of the things we can do as an engineering community to improve this situation. So the limiting factors I talked about last week were a work-life balance challenge. It can be difficult to work in a stressful engineering job and then still have time for a life outside of that, whatever that life might look like. There's a perception that the culture is unwelcoming, which from my experience is for the most part not true, but there are some small groups or small projects that can be unwelcoming. There's a perceived lack of career mobility. Women believe that they're not going to get promoted at the same rate as men. There's a negative industry image. There's a gender imbalance in education, which creates this circular problem. And then there's maternity leave that impacts promotion and re-entry after leave. So what can we do as an engineering community to increase the number of women in engineering roles? How do we make engineering more desirable to everybody? I have a list of about 10 improvements that we can make as a community. Some of these might work better than others for certain companies. Some might be better for certain people. And this list is definitely not exhaustive. It's just meant to help us think about what ways we can be more inclusive. So, dedicated training and certification for women. And this could include women networking events. This isn't to say that we need to have separate professional development for men and women, but that some women might feel more confident to contribute to a discussion when they feel they have a safe space to do so. I was listening to a woman in engineering panel recently. It was one of the National Engineering Month events going on. And one of the things they talked about is a lack of confidence from females in STEM. Not because they aren't capable or generally confident people, but because entering a male-dominated industry, you feel like you have so much to prove already. Like you can't make mistakes, you have to be perfect, or they'll just write you off. And whether or not that's accurate, I think that's what a lot of women in engineering perceive to be the case. Increasing youth interest. This includes engineering and science programs in school to get young female students interested in potentially a career in engineering. Improving hiring practices to make them more inclusive. I fully support having to hire the best person for the job, but how can we modify our workplaces and our hiring strategies to make it more appealing for female applicants? Saying, oh, there aren't any female applicants, so we don't hire many females, isn't a reason or an excuse. Why aren't there any applicants? Are you an inclusive workplace? One that women want to work at? Closing gender pay gaps. This is just so stupid. I don't even understand why there is a gap. Another important thing that we need to do is combat sexual harassment. We need to define clear policies. This includes blatant sexual harassment, but it also includes things like men thinking they can call women sweetie, which don't do it. It's degrading and it's very annoying. Another thing we need to do is invite women to participate in the decision-making process. You'd be surprised what ideas come out on the table when you provide a safe space for people to brainstorm. As I said earlier, having a diverse group of people at the table is going to improve the ideas that come out of that discussion. Another item we need to address is work-life balance policies. A problem that I've noticed in North America is that we almost celebrate being overworked, like being tired and exhausted from your job and working so many hours that you can't do anything else is a badge of honor, and we brag about it. I myself am guilty of this, but that is not the piece to brag about. The piece to brag about is being able to balance your work and your life, being able to have both, have your cake and eat it too. And we need to put in some policies to protect people because burnout is real. Not only do we push people to that point, but then we don't support them when they get there. So some ways we can do that are to limit overtime, no weekend work, allow overtime to be used in lieu for vacations, and just managing people's workload a little bit better. That comes from management giving too much work to people, and that also comes from people accepting it. I know that sometimes you feel forced into taking work that you know you don't have time for, and you don't always have the ability to say no. But I do think it does take a communication from both sides to say, no, I can't take on that project. I already have too many things on my plate. And then the managers need to listen to that and understand that they're telling you where their boundary is. And if you keep pushing, you're crossing that line. We also need to diversify promotion shortlist. Don't just promote the people you're friends with. Promote those you think will make a difference. And also don't just throw people into the fire. We can't just put people in these roles that they've never been in before and just wish them good luck and hope for the best. We have to help people. We have to guide them. We have to give them tools to succeed. I also think that different people manage different ways. I myself am somewhat new to a management role, and I've watched a lot of managers before me just yell and scream until they get what they want. And I don't really think that works because then people are scared to talk to you. So I try to stay really approachable. I try to have a conversation about them. I try not to embarrass anybody. If I do need to have a difficult conversation with someone, I definitely do it in private. I try to support them. Them succeeding not only makes the whole team successful, but at the end of the day, it's also less work for me to have everybody on my team be successful because then I don't have to clean up any messes. So it really works well for everybody to provide support and guide the team to be the best that the team can be. So that's a list of things that we can do to increase the number of women in engineering and improve our community. It's by no means an exhaustive list. I'm sure there are many more things we can do. Please join me next week for part 3 of this segment, where I talk about Engineers Canada's 30 by 30 plan to increase the number of newly licensed female engineers to 30% by 2030. This may seem like a small goal, but it's not, because the number of newly licensed female engineers is currently at 17%, and it's been that way for the last 5 years. So they're effectively trying to double it, which is a huge goal. But more on that next week. Let's get into the engineering failure. What went wrong on the Hancock Tower in Boston, Massachusetts? Now on to this week's engineering failure, the Hancock Tower in Boston, Massachusetts. The John Hancock Tower, more commonly known as the Hancock, was named after the insurance company that built it, which was named after John Hancock, whose large and conspicuous signature on the U.S. Declaration of Independence led to John Hancock being a colloquialism for the signature. The tower is 62 stories, 240 meters tall, and has a floor area of over 190,000 meters squared. The architect was Henry Cobb from I.M. Pye & Partners, and it was supposed to be constructed from 1968 to 1971, but it didn't finish until 1976, 5 years later. The cost also increased from the original budget of $75 million to $175 million, more than double. The schedule and cost overruns were due to some design flaws that I'm going to get into shortly. Despite all that, in 1977, just a year after it opened, the American Institute of Architects gave the building the National Honor Award. And in 2011, the building also received the 25-year award, which is given to buildings that set a precedent for the last 25 years and set a standard for architectural design. Even today, the Hancock is still the tallest building in Boston and New England. This is due to a few different factors, some of which are wind and shadows. There's low demand from the tenants for tall towers, but mostly it's due to downtown's proximity to the Logan Airport. I've never been to Boston, but looking it up on a map, the airport is right downtown, which is extremely rare, for North America at least. I'm definitely surprised they haven't moved it. Fun fact, New England isn't a state, it's a region. It includes Connecticut, Maine, Massachusetts, New Hampshire, Rhode Island, and Vermont. Americans love their regional nicknames. Don't even get me started on what they consider the Midwest. Spoiler alert, it's not in the West, or even the middle. The Hancock has a minimalist design. It has the largest possible panes of glass, and there's no spandrel panels, so all of the glass is vision glass or see-through, and the mullions are minimal. The floor plan is a parallelogram or rhomboid shape. It's like a rectangle, the opposite sides are parallel, but they're not at right angles, so it looks like it's slightly leaning to one side. This makes the corners appear sharp. As well, the short sides have deep vertical notches. The glass is highly reflective, and it's tinted slightly blue, so it's a subtle contrast with the sky on a clear day. You really have to see this in the pictures. There's a link in the show notes to pictures from this episode, or you can look it up. The glass is so reflective that under certain conditions, it almost blends into the sky. I chose this failure because I found the windows falling out of the building to be a very interesting failure, but that wasn't the only problem with it. I never really know what I'm going to find when I start researching, and I'm often pleasantly surprised. I guess it pays to be curious. Information on this building was limited. There was a settlement in 1981 that prevented all parties in the design and construction from speaking about the building's problems. This is pretty common. No one wants to scream their mistakes from the rooftop. But it is important to share this type of information with the public so that lessons can be learned and future mistakes can be prevented. Alas, our education is not their responsibility. They are free to do as they choose. And besides, there's still enough information out there to get a general understanding of what went wrong. The three main failures I'm going to talk about today are the excavation, the building's glass, and the structure. The Hancock is built in an area of Boston called the Back Bay, which is reclaimed land in the Charles River Basin that was infilled in 1859. Think like the Palm Tree Islands in Dubai, or even some areas of New Orleans that I talked about in the second episode. The Hancock is located only 7 or 8 blocks from the river, and I imagine the water table is quite high in this area, making excavation challenging because there can be a lot of water to manage and the ground can be somewhat unstable. In order to construct below grade levels, the contractors have to first dig a hole. To keep the sides of that hole from collapsing into itself and keep the ground and surrounding structures stable, temporary retaining walls are constructed around the perimeter of the hole and pinned into the ground to keep the hole and pit from collapsing. However, during construction of the Hancock, the retaining walls warped and the pit filled with clay and mud, damaging nearby utility lines, sidewalk pavement, and nearby buildings. Trinity Church, which was located across the street, successfully sued the project for $11 million to pay for the repairs to their building. As I mentioned earlier, the glass on the Hancock is reflective and creates a subtle contrast with the sky. The glass was constructed in 1.2 meter by 3.4 meter panels that weighed 227 kilograms each. During construction, before the building even opened, several glass panels cracked and at least 65 of them detached and fell onto the sidewalk below. Police had to close streets surrounding the tower whenever the wind was 70 kilometers an hour or more. Things falling off of buildings is a serious issue. I've seen some towers put up nets around the structure to contain material, and others develop a rigorous system for tying materials down. Story time again. This one has stuck with me, and it's been almost 12 years now. It was August 1st, 2009, and a large 6-meter piece of corrugated metal building material flew off of the top of an 18-story building under construction in Calgary. A 3-year-old girl was killed instantly, and her father and 7-year-old brother were sent to the hospital with non-life-threatening conditions. The developer and builder were charged with violating the Alberta Safety Codes Act and allowing an unsafe condition. They were fined $15,000 each, which really isn't enough, and some improvements were made to regulations and weather detection. This little girl's life was over, just like that, because someone didn't tie down a piece of metal. If you've lived in Calgary for any length of time, you know that the weather can shift on a dime, and you have to always be ready. Sometimes I leave the house preparing for all 4 seasons in one day. For those listening outside of Calgary, this is not global warming talking. It's mountain living, causing Chinook winds that can bring in warm weather in the middle of the winter, causing temperature swings from minus 20 degrees Celsius to 10 degrees in a matter of hours. It's honestly a fascinating phenomenon, but this episode is not about weather. Let's get back to the Hancock. Frank Durgan of MIT's Wright Brothers Wind Tunnel built a scale model of the entire Back Bay and an aeroelastic model of the Hancock. His results raised questions about the structural integrity of the entire building and found an unanticipated twisting of the tower. As the building swayed and twisted in the wind, the glass has to move with it, except that it didn't. The glass was so rigid that it didn't allow for movement within its own assembly. The double-pane reflective glass had a thin strip of lead between the two layers of glass, and over time that lead had developed metal fatigue. The lead strip's bond to the glass was so strong that as it cracked, so did the coating on the glass, and eventually the glass itself. In October 1973, the architect announced that all 10,344 panes of glass would be replaced with single-paned, heat-treated panels, the same kind used in safety doors. This cost about $5 to $7 million. 5,000 of those panes were removed intact and offered to artists for future projects. During diagnosis and repair of the glass, plywood replaced many of the missing panes. Because of this, the building was nicknamed the Plywood Palace, the Plywood Ranch, and the world's tallest plywood building. When the building swayed and twisted, the upper floor occupants suffered from motion sickness. That must have been a lot of movement. To counteract this, 2 tuned mass dampers were installed on the 58th floor. The City Court building covered in episode 1 had a tuned mass damper as well. The tuned mass dampers at the Hancock are 2 136 metric ton weights at opposite ends of the 58th floor. Each weight is a box of steel filled with lead. They're 5 meters square and 1 meter tall. The box rests on a steel plate covered with lubricant, and the weight is free to slide. The weights are attached to the steel frame of the building by springs and shock absorbers. As the building sways, the weight stays still and the floor slides under it. Then the springs and shocks pull the building back. The reason for 2 weights is that they tug in opposite directions when the building twists. The tuned mass dampers at the Hancock cost an additional $3 million. Despite the tuned mass damper, the building could have still fallen over under certain wind conditions and loads. The experts believe the short sides would fail first. I think this comes from the wind forces being exerted on the long side, which was kind of like a sail, and relying on the short sides to keep the building standing. But if you hadn't predicted the wind forces, or even underestimated them, the short sides would not have been designed with the reinforcement to support the building. 68 metric tons of diagonal steel bracing were added to the narrow sides at a cost of $5 million. As I mentioned earlier, there was a settlement that prevented anyone involved in the tower from speaking to the public about what went wrong and who was to blame. However, I found a New York Times article from 1988 that interviewed a local engineer and architect that were on the periphery of the project but not bound by the settlement. The local engineer was none other than William LeMessurier, the structural engineer who designed the City Court building in New York City that I covered in episode 1. The architect was Victor Mahler, a glass curtain wall specialist who used to work at the architecture firm that built the Hancock. As we know from the City Court building design, which took place a couple years after the Hancock, the building codes and science of testing the effects of wind on large, tall structures was kind of just in its infancy in the early 60s and 70s. And Henry Cobb, the architect of the Hancock, was just a bit ahead of his time in terms of how his creative designs could be successfully realized in the real world. The Hancock was bought from John Hancock Insurance by Broadway Partners in 2006 for $1.3 billion. But in 2009, they defaulted and the building went into foreclosure. On March 30th, 2009, the building was sold at auction for $660 million to Normandy Real Estate Partners and 5 Mile Capital Partners. In October 2010, Boston Properties bought the building for $930 million. Both the name Hancock Tower and the insurance company's lease would expire in 2015. The building was officially renamed in mid-2015 to 200 Clarendon, but I assume most of Boston still calls it the Hancock. One more piece of information on the building that I found interesting. It's not related to the failure at all, but it's about the observation deck at the top of the tower. Whenever I visit a city, I usually go to most of the observation decks, which is interesting because I'm afraid of heights. But they provide such a really cool view of the city and the surrounding area that I just can't miss it. The observation deck at the Hancock was closed after the terrorist attacks on September 11, 2001, which is understandable. However, the observation deck remains closed to this day. The owner cites security as the reason, but they've rented it out for private functions and expressed intent to replace it with office space. The part that I find interesting is that the city officials claim the deck was a requirement for the original building permit so that the public could gain a benefit from the high tower. That said, the officials haven't been able to locate the documentation to support this requirement and haven't been able to force the owners to open the observation deck. So there you have it, the Hancock Tower in Boston. A lot of things went wrong that delayed completion for 5 years and over doubled the budget. Despite all of that, the building still received architectural awards for its design. And I really can't say I disagree with that. Between its height against the Boston skyline, the way the glass causes it to almost blend in with the sky, and the interesting floor plate shape, I myself am a fan. I mean, nothing is perfect. Every single project I've ever worked on has had some issue or another. Maybe not as serious as glass falling off of it, but something always goes wrong. And the more complex and different the building is, the more things are likely to go wrong. Sure, we could rinse and repeat simple projects with little issues, but where's the fun in that? Plus, they'd all look the same, and that would be boring. Like I've said before, the trick is to flush out all the issues on paper, but never stop reaching for the stars. For photos and sources from this week's episode, head to failureology.ca. There's a link in the show notes. I've also included links for sources from the Women in Engineering segment. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find it. If you want to chat with me, my Twitter handle is @Failureology. You can email me at thefailureologypodcast@gmail.com, or you can connect with me on LinkedIn. Check out the show notes for links to all of these. And tune in next week to hear about Dieselgate. Engineering failures are bad enough, but this one was done on purpose. But more on that next week. Bye everyone. Talk soon.